Sampling distributions for means. This is Unit 7, which is Chapter 18. Okay, we're going to start by talking about what a sampling distribution of the means is. So a sampling distribution acts as a frame of reference for statistical decision making. Random samples rarely exactly represent the underlying population. So we rely on sampling distributions to give us a better idea whether the sample we've observed represents a common or a rare outcome. So a sampling distribution of the mean is a probability distribution of means for all possible random samples of a given size from a population. Basically what we're going to do is we're going to take a whole bunch of samples. We're going to use those samples and plot them, make a distribution, find the mean of that, and then put all the means together. So I'm going to kind of give you an example of what that looks like. So here is SAT math scores. So we're going to take a sample of 10 random students from a population of 100. So you might get a mean of 502 for that sample. Okay. Then you do it again with a new sample of 10 students. And for this sample of students, your mean might be 480 this time. Then you do it again and again and again, and you get the following means for each of those 3 new samples of 10 people. Okay, so the first one, you got whatever, 502, then you got 480, and then you get 550, then you get 517, and then you get 472. So every time you take a sample of 10, you're going to get a different mean for that sample. All right, so what does that look like? So here they have a graphic, which if you look up here at the top, this top part of it says the distribution of one sample. So with that, that means that, you're going to go through and you're going to look. They said that if we took one, right, you had it says a mean of 497 there. And then they did another one, distribution of sample 2 had a mean of 509.92, or approximately, 510. Then we go through and we look at sample 3, they had a mean of 506.02, and then again for distribution 4 had a mean of 491. Okay, so, this is, they took 10 people, right, and they took the mean of that sample. So then what they did is they said, okay, so here's the distribution of sample means. So what they did was they found the mean, right, which is this 497, and they're going to plot it. Okay, so this is the mean from one. Okay, and then they're going to go ahead and they're going to put the mean for the other one. So this was, about 510. So you can see how it's a little bit higher up. This was the 497, now we got the 510. Well, now we got one that's about 506, so that one is going to make this one bigger here, right? So you still have the 497, and now you have these two, the 510, 500, and about 7. And then the last one was 491. So that's where this one comes in, where it's a little bit less. So what they're doing is now we are making a distribution of all the means from our samples. So the first ones up here at the top, this is just your individual. You're taking a random sample of size 10, and you're getting the mean of that sample. And then the distribution of sample means is when you're taking the means from each one of those random samples that you take, and now you're making a distribution of that. And so then if we kept doing it over and over and over and over again, which is what you would do, this is what you would end up getting. So you would end up getting a distribution that looks like this. Now you're going to see that it is, approximately normal, which is usually what happens once you do things, over and over and over again. So this is from taking all those random samples of size 10 and then plotting the means of all those distributions. So kind of a good visual of what is actually happening. Okay, so here is the vocabulary that goes with sample means. So first of all, with sample means, we have mu, right, which is this symbol, and then we have sigma, which is the standard deviation. So those are our population parameters. Then we have X bar and S, and those are our sample statistics. And then we have the mean of X bar, and so the mean of X bar is the mean of the sampling distribution. So that is the mean when you take all those means and put them together. And then you have the standard deviation of X bar, and that is the standard deviation of the sampling distribution. So, you know, kind of like this is how you can kind of go through and figure out what they're talking about, right? The mu and sigma are about the entire population. The X bar and S are about a single statistic. So that is when you took a random sample of size 10, right, your X bar. And then this is the mean of X bar. So this is the mean of all those X bars that you're going to plot. All right, so how do we describe a sampling distribution? So we're going to describe a sampling distribution using CUS, right, like we did before. So we have our center, which is the mean. So that is the mean of X bar, which is actually just mu, which is kind of a great phenomenon. What happens here is that, you know, the mean of the sampling distribution is going to actually equal the mean of the population, which is actually a very cool thing. So the shape is going to say that it will be the same as the population shape for a small sample size, so it will mirror whatever it is. And then it will be approximately normal if a large enough sample size is taken. So what do they mean by large enough, right? So by definition, if n is bigger than 30, so if it's bigger than 30, then what happens is our central limit theorem, which we're going to talk about in just a second, kicks in, and the sampling distribution will become approximately normal based on the central limit theorem. Okay, and then our spread for the standard deviation, which is the standard deviation, is the standard deviation of X bar, which is the population standard deviation divided by the square root of n. Okay, so here's the central limit theorem. So the central limit theorem says when the sample size n is sufficiently large, and remember that we define sufficiently large as greater than 30, the sampling distribution of sample means is approximated by a normal curve, even if the parent population is not normal. So if you take a big enough sample size, then you're going to deal with a normal curve, which is what you want in statistics, right? We want to go back to our normal curve, so therefore we can calculate probabilities. All right, so here's just a visual of the central limit theorem. So over here, you know, these little pillows, these are our parent population. So remember back at the beginning, we talked about different shapes that we can have. So we have, you know, our symmetric shape, we have skewed left, we have skewed right, we have, you know, we even have a uniform one back here in the purple. You can have bimodal, unimodal, whatever. So what the central limits theorem says is that if you take a sample size big enough or large enough, which we say by 30, right, then no matter what the parent population looks like, whether it is skewed left, skewed right, uniform, bimodal, whatever, the sampling distribution of sample means will become approximately normal, no matter what the parent population looks like. So if you have a small sample size, though, it will mirror what the population was. All right, so now we're going to look at an example for mean. So it says, suppose that the mean value of interpapillary distance for all adult males is 65 millimeters, and the standard deviation is 5 millimeters. If a random sample of 45 adult males is selected, what is the probability that the sample will be between 64 and 67 millimeters? Okay, so we're going to start with our little chart just to kind of help us organize our thoughts. So first thing that we're going to do, step one, okay, is we're going to write down the mean. So I'm going to write down mean and standard deviation. Okay, so remember that the mean for sample means it's mu and then subscript x bar. So the mean of the sampling distribution of sample means is equal to the population mean, which is going to be in this. It says suppose that the mean value for the distance for all adult males is 65 millimeters right here. So this is mu. So I'm going to put 65. Okay, so then I need the standard deviation. So the standard deviation for x bar is equal to the population standard deviation over the square root of n. So if I keep reading in, it says that the standard deviation is 5 millimeters. So this is sigma. That is our population standard deviation. So that means that I would put 5 on the top, right, divided by the square root of n. So going back, it says if a random sample of 45 adult males, so this right here, 45, this is going to be our n. So I'm going to put 45 here. So I'm going to have 5 over the square root of 45, and then that is going to be, if I go ahead and put it in my calculator, I get 0.745. Okay, so that's the mean and the standard deviation. Okay, so box number 2 over here is going to be our conditions. So, first of all, you have to decide, right, 1, so you have 2 things, A, that it came from a normal population, or B, that our sample size is bigger than 30, so by the central limit theorem, the sampling distribution is approximately normal. So, it doesn't say anywhere in the problem that it came from a normal population, so that means that we can't use option A. But we can look at option B because our n is 45, right? So that means that by the central limit theorem, this is going to be approximately normal. So what we're going to say is since n is greater than 30, right? So n was 45, so it is greater than 30. By the central limit theorem, sampling distribution of sample means is approximately normal. Okay, so now we know that we have a normal curve. So now we can go ahead and go down to number 3. Okay, so number 3, if it didn't meet the conditions, right, if you weren't allowed to use the normal distribution, then you couldn't calculate the probability. Well, actually, you could calculate the probability, it's just not going to be accurate. Okay, so now what we're going to do is we're going to write what is called a probability statement. Okay, so we're going to write it like this. So we're going to write, we want the probability or the proportion, right? And then it's going to be, in this one, we're saying what is the probability that the sample will be between 64 and 67 millimeters. Okay, so since this is a between, that means our x value is going to be in the middle. So we're going to put 64 is less than x, which is less than 67. Okay, so now the whole purpose, right, that we wanted it to be approximately normal is so that we could change these into z-scores. Okay, so I'm going to kind of write over here what that z-score formula is, just to kind of help you remember. Remember that we use x minus the mean divided by our standard deviation. So we have a mean here of 65. We have a standard deviation of 0.745. These are our x values, so we're going to convert them into z-scores. So I'm going to write it as a z-score change this to a z-score. So I'm going to put probability, and then I'm going to put 64 minus the mean, which is 65, divided by the standard deviation, 0.745, which is less than, and I'm going to change that to a z because I'm converting them to z-scores. And then I'm going to take 67 minus 65, and then over 0.745. Okay, so now I've written the probability statement. So that means step 4 is going to be to calculate the probability. Okay, so just kind of a refresher on that. When we're calculating the probability and we've changed it to z-scores, we're going to go to normal CDF. So, you know, our final thing, you actually don't, you can leave it in this red part right here. You can leave it like that. And then the last thing that you would do is you would go to normal CDF in the calculator. And then you're going to put in two things. You're going to put in the left and the right. This one, because it's in between, you're going to put in the two z-scores. So the bottom z-score would be negative 1.34. Top z-score is going to be 2.68. All right, and then that is going to give us 0.906. And so, you know, the probability that the sample will be between 64 and 67 millimeters is about 90.6%.